unless there are specific questions, I wanted to look at some of the free response that you'll see on the test, or if you have specific questions about the quiz. The free response will help you for the quiz some. Want to do that? Is that okay? Yeah, so let's look. What's that? Okay, what? It doesn't help you directly because you won't see these questions on the quiz, but the content will be on there. Let's see. So your free response on the test. Well, where is it? Oh, here it is. Looks like this. This is, by the way, spring 19, I think. Yeah, this is spring 19 free response questions. Your free response are going to be almost identical to this. I mean, not the numbers and the orientations, but the type of questions that you'll have will be very, very similar. So first, that's electric field. Never mind. I told you might have a force problem. It might actually be a field problem. They're very, very similar. Don't let that freak you out right now. Let's instead do, this is spring 19. We'll do some of these multiple choice. So this will be a direct help for the quiz because your questions will be like this. This is spring 19, number 2. Okay. So if you're new to these, I'm going to try to pull from exams that we don't have in your workbook. I think you have spring 16 in your workbook or 15. I won't do that because we'll use those in class for extra practice. All right. So I want to know the magnitude between the force Q1 and Q2. These multiple choice questions are actually not that difficult because really the only tricky part is you have to figure out what is the distance between them. And so in order to do that, I just recognize that this is a triangle. And it is particularly a 3, 4, 5 triangle. And then I can calculate what is the force because the force is going to be equal to K, Q, Q, over r squared. And in this case, r is 5 meters. So this is 9 times 10 to the 9th. That's my Coulomb's constant. Q is going to be 25 times 10 to the minus 5. Q1 is 2 times 10 to the minus 4, divided by the distance, which is 5 squared. Remember, I said I try to make the numbers easy. See how the numbers here are pretty easy to work with? Because I have a 10 to the 9th here, and that cancels out with the 10 to the negative 5 and the 10 to the negative 4. Y'all see how that works? It's like 10 to the 9th divided by 10 to the 5th, 10 to the 4th. And 10 to the 5th times 10 to the 4th is the same as 10 to the 9th. When I multiply exponents like that, I add up the exponents. And then also here I have 5 squared. That cancels with the 25. So really I'm just left with 9 and 2 are 18 newtons. You should be able to do most of my tests without a calculator. Okay? Good example. You'll have a question like that on the quiz. Absolutely. Count on it. It'll be there. Let's look at number 4 while we're on this page because students sometimes get confused about these. We did one in class like this today. It was similar to this. Remember I said that, oh, look at the old test, that there are variations of this problem, and not just with forces, but also with fields, which we'll get to next week, and then potential, which we'll get to, I don't know, later, maybe next week. So here I want to know, is it possible to place a charge at one of the marked locations and have it experience 0 force? And then which location is that? Most of the time on these, the sign of the charge doesn't matter. So let's just start with a positive charge and ask ourselves, what is the force on that positive charge? So I have my minus 4q. Let's say that I put a positive charge here. Then the forces that act on it, I'm going to have a really big, look, I'll draw the force for this charge in red, the force due to this charge in blue, and the force due to that charge in black. Due to the minus 4q charge, it's going to have a really big attractive force because it's a big charge and it's really close to it. The force gets bigger the closer you get, and the force gets bigger the bigger the charge is. Remember, F was right here. If Q goes up, F goes up. If R goes down, F goes up a lot. That's an inverse quadratic relationship. But if I look at the other forces, there's a repulsive force due to this charge, but it's itty bitty because it's farther away and that charge is smaller. And then likewise, for this charge, it's itty bitty too. So I definitely cannot get a zero force at A. Now that we sort of know how that works, let's look at the other points. In general, on these, you want to get as far away as you can from the big charge, and that way the force due to the bigger charge will be minimized because it's farther away. So let's look at, say, I don't know, point D and see if that works. Let's imagine that I have a positive charge right here. Are y'all with me what I'm doing here? I'm going in, I'm drawing vectors for the forces due to all of those charges. But I'm also drawing them relative to one another so that the size of the vector is related to the size of the force. If the charge I'm dealing with is a big charge, that makes it a bigger force. If the distance is small, that makes it even a bigger force. So let's see. Let's do the minus 4Q. Now, minus 4Q is a big charge, but it's far away. So I have a force that's relatively small. Likewise, I have these two other charges that are small, but they're close, so they're going to be bigger. I don't know exactly what they're going to be, but they're going to be bigger than the red charge. Or excuse me, not bigger. They're going to be smaller because the charge is smaller, but they're going to be bigger. You know, because the charges are closer, that makes the force get big, but because the charges are small, that makes the force get small. So you sort of have these two competing ideas. So it seems like that would work because I have this charge due to the force due to the minus 4Q that is minimized because it's far away. And then I have the forces due to these other charges that are small, but they're close. So that makes those forces bigger. Let's look at C, though. You want to practice these, okay? These types of problems often trick students up. But with practice, you can get them. Let's look at C. So I'm going to put a positive charge here. Notice that the blue and the black are going to cancel one another out. Right? They cancel one another out because they're equidistant from charges that are of the same magnitude. But the 4Q is still going to be there. So I can't get a zero force there because the blue and black cancel one another out, and the red force still is there. Now let's see. At B, what do I have? I have a force due to the minus 4Q that is really big. And then I have forces, I'm imagining a positive charge right here. What is the blue arrow? What direction is it going to go, left or right? It's going to go left because it's a repulsive force. So it's going to go in this direction. And then the black is in the same direction. It's smaller because it's farther away. So no zero force there. The only possible place to get a zero force is at point D. That's the procedure you want to go with on these types of problems, is that you just step through each point and ask yourself, okay, what is the set of forces here that I'm dealing with? Or later when we get into field and potential, you'll do the same thing. Okay? Are those tricky? They are. They are a little bit tricky, and they require, you know, a lot of thought to go into them. But that's also what makes them really good questions, that you have to think about them a lot. All right. That's electric fields. Number 9. I was working with a student earlier on number 9. Let's look at it. You have 3 neutral conducting spheres and a charging device that allows you to place charge Q on any neutral object. You want to have 2/3 Q on each sphere. How do you proceed? Now, you could go through and read each of these and think about the result of this. Like for example, would be I have 3 spheres. I put Q on sphere number 1, and then I touch it to sphere number 2. When I do that, what I get is I'll get my 3 spheres again. I would get Q over 2 here and Q over 2 here, right? Because it splits that charge up when I touch those 2 spheres together. But then it also says to touch the sphere 2 to sphere 3. So then if I touch this sphere to this one, it's going to split it again. So those bottom 2 spheres are going to have what charge on them? Q over 4, right? Because it halves the charge. So I don't have the result, which is what I want, are 2/3 Q. So you want to go through each option. Do y'all know what the answer is? A is the answer. Very good, Elise. So A, I charge 2 spheres, each with a charge Q. Look, have it right there. And then I bring all the spheres together, and it's going to redistribute those charges so that they're evenly distributed between the 3 spheres. So if I take 2Q and I divide it between 3 spheres, that gives me 2/3 Q on each sphere. Listen, what this is testing, the idea that this is testing is first that charge is conserved, that you never lose charge, that whatever charge I'm starting with, I keep that charge all the time, the conservation of charge, and then also on a conductor, the charge is evenly distributed. And we had this picture in class where I said, oh, if you get charges on a conductor, what's going to happen is that those charges will be evenly distributed. That happens here too. When I touch these 3 spheres together, they each get 2Q divided by 3 on those spheres. So they'll be evenly distributed on the sphere. Okay, you're going to have some questions like this. I think these are pretty easy. Well, they're not easy if you don't know how to do them, but the ideas behind them are not difficult. What can you say about the charges on these 2 charged balls? They're the same, right? They're either positive or they're both negative. But so make sure that you get that it's either or. Okay, this other stuff is new. We'll wait for that. Okay, number 4. I think we did a problem like this today. I'm not sure. I did it with a student earlier. I don't know if we did it in class. Oh, goodness. Gosh. My wife, have I ever told y'all this? My wife has the loudest sneeze that I have ever heard, but not anymore. Can we just take a little, like a segue? Because she used to sneeze so loud. And in the car while we were driving, and it would just hurt my ears. And finally one day I told her we've been married for a lot of years. And my eyes were like, man, actually we've been married for about 6 months maybe. Felt like a long time because of her sneezes. I was like, gosh, Kazi, your sneezes, they just hurt my ears. And it sort of hurt her feelings right at first. But then she started stifling her sneezes, which I don't like that either, you know, because you gotta let that thing out, right? But now she sort of reserves her sneezes for when she's not around me. We just celebrated our 18th anniversary. 18 years, sneeze-free. I don't do anything annoying. I swear, nothing at all. You don't believe it, do you? Huh? Yeah, I'm joking. I do lots of annoying things. Okay, so here, what vector best represents the net force on the bottom plus 2Q charge? When you get this problem, which you will, it will be on the test, you draw the 2 component vector, or the 2 vectors from the other 2 charges, and you draw them relative to one another with the right perspective. So for example, I know that I have a charge that is repulsive in this direction due to that plus 2Q charge. And then I have a charge that is attractive that's twice as big for that charge. So that tells me then that either A or B is going to be the answer, because the resultant of those 2 vectors has to lie in between the 2 vectors somewhere, right? You think of a guy's pulling ropes in these directions, they're going to make the thing move in this direction. So it's either A or B. Which is it? B is right, because the resultant vector will be closer to the bigger vector. It's like it'll pull that vector over closer to the longer vector. Oh, number 5 is a good one. This comes straight from the concept test. If I experience a force of 18 newtons and then I triple the distance, what is the new force on the charges? If the distance first is getting bigger, what's happening to the force? Is decreasing, so I know it can't be that, or that, or that. It either has to be B or E. Always do that on multiple choice exams. Go through and get rid of the ones that don't make sense. So which is it? E. And that's because it's a quadratic relationship, not a linear relationship. That is that F is proportional to 1 over r squared. KQQ over r squared. So if I triple this value, I 1/9 that value. So 1/9 of 18 is 2 newtons. We did this last semester, right? We have these exact same problems. It's just they were talking about different relationships. So if you got it last semester, fortunately, you're going to see some of the same things this semester. If you didn't, then that just, unfortunately, you get another chance to get it. All right. Okay, oh, number 6. I love these problems. So this is like the one we did before. So I'm going to talk you through it. I have a -2 coulombs and a +3 coulombs. And there's a point C in between them that's in the middle, that's equidistant from those 2 charges. Point C is not a charge, that's just a point in space. I want to place a 3rd charge, so the net force on the 3rd charge is 0. What must be the sign of the charge, and where should it be placed? Let's just start playing around. I think I don't know what the answer is. I'm just going to play around. I'm going to say, well, what if I put a well, let's see. Actually, let's look at let's go through the options. So should it be positive and to the right of the +3 coulomb charge? So what happens there? If I put a positive charge there, I get a really big force due to this charge, and I get a really small force due to this charge. Because the small charge is smaller and it's farther away, so that makes a smaller force, not A. Let's go look at B. Positive and to the left of midpoint C. So a positive charge right here. What does that give me? It gives me a force in this direction. And now I'm farther away from the 3 coulomb charge. So it should be like that, in that direction. That might be the right answer. Let's hold on to that. I think it might be, and we'll look and see if there are any others that, yeah, Emily? Oh, you're right. I did that wrong, didn't I? Not to the right, to the left. Right? Yes, no, you're right. You're absolutely right. So B is not the right answer. Y'all see what she said? That there's a repulsive force from the +3 coulomb and an attractive force to the -2 coulomb. So not that one, not that one. Either negative or positive and to the left of the -2 coulomb charge. So let's have a positive charge over here. I'm going to have an attractive force to that one and a repulsive force from this one. Notice it's farther away from the bigger charge, so that force is minimized even though it's a bigger charge. That one might be right. Let's hold on to it and look at the others. So I'm just going to put a little question mark. Negative and to the right of the midpoint C. Have a negative charge there. It's repelled from this one and attracted to this one. Can it be D? Not D at all. And to the left of midpoint C, either positive or negative. I'm just going to do a positive. It's attracted to this one. It's repelled from that one. So it can't be that one. So it has to be C. Okay? Practice with those. You'll see different variations in the other exams. But you'll probably see one, well, probably on the quiz. Well, maybe on the quiz, but definitely on the exam. There's a similar one, but it has to do with electric fields. Oh, I don't think we've done one like this. So number 17, this is still spring 18. Number 17, spring 18. I want to know if cube B has a negative charge, what does that tell me about the charges of cube A and cube C? Almost always have a question like this. Cube C, for example, can have a force that is either in this direction or in this direction. However, to get a vector that's here, I'm going to need to have one of its components to be right here. So this vector I can just get rid of. That means that cube C has to be positive. Where does the vector between B and A need to point? Up or down? It needs to point up, right? So that means if this one's negative, A has to be positive, right? So C then is the right answer.
Wait, how did you find that Q is positive?
Let me erase it again. So cube B, I'm told, is negative.
Okay.
And I know that the two vectors, in order to get this vector, the two vectors have to be here and here. And then the vector in between is the resultant. And since they're both attractive forces, both of these have to be positive. Okay? Good. Y'all tell me what the answer is for 18. Read it and tell me what you think it is. Has to do with conservation of charge. All right, any thoughts? Not A. Who said that? Megan, that's Megan? That's right, it's -4. Because look, I have a total of -3 coulombs here. Remember, charge is conserved, right? So that means that my total still has to be -3 coulombs. In order to get -3, this has to be -4. So B is the right answer, -4. Okay? We did one of these in class, but the allowable charge, remember, an allowable charge is a charge that is an integer number of fundamental units. And the fundamental unit of charge is 1.6 times 10 to the minus 19 coulombs, plus or minus. Plus is a proton, minus is an electron. So for example, this is 1 proton. This is 2 electrons. This is 2 protons. This is a lot of protons. In fact, if I do 10 times 10 to the minus 6 divided by 1.6 times 10 to the minus 19, micro is -6, right? What was it? 1.6. I get 6.25 times 10 to the 13. Is that an integer? 6.25 times 10 to the 13? It has a decimal point in it, though. Is it an integer? Are you sure? Right. It's 6, 2, 5, and 11 zeros. Right. That is an integer. So that's just a whole bunch of protons. So it's not A. It has to be B, which is like 1 proton plus 0.6 protons or whatever, plus a little bit more. Not 0.6 protons, but a little bit more. Yeah.
So like, you only divided the top one because it's micro?
No, I divided them all, but I divided them all in my head. So like, for example, E, I said 3.2 times 10 to the minus 19 divided by 1.6 times 10 to the minus 19. That's equal to 2. I can see because these cancel out, and then this is just equal to 2. All right, But you're looking for one that does not equal to an integer value. Be careful because students often look at this number and say it's an integer, but really it's not because it's got all these zeros behind it. A conductor, just sort of know what a conductor and an insulator is. Which is it? The protons move freely? No, that's not right. Which is it? Ah, man, that's a trick. Like E, whoever puts E is the answer. But sometimes none of these is an answer, so make sure you're aware of that. The right answer is because it has electrons that can move freely. Okay, conduction electrons. That's all new stuff. We'll get to that. Particular questions that y'all have? Ooh, this is a good one. The court, did we do a court question in class?
Yeah.
We did. It was different from this, though, I think. It wasn't the same one, was it? Oh, let's try. Oh, yeah. So you do it the same way, except you're looking for a combination of these that add up to plus 1e, which is a proton. When you encounter these types of questions, I just go through the options. Up is 2/3, plus down is minus 1/3, plus minus 1/3. That's equal to 0. So this, up, down, down, is a neutron. That's not the answer because I'm looking for a proton. Let's try the next one. Up, up, down. That's 2/3 E plus 2/3 minus 1/3. What does that equal to? 1. Right, so that's my answer because a proton has a charge of 1 fundamental unit, 1.6 times 10 to the minus 19, or 1 E. With that idea here on number 6, we haven't seen one like this, but you should be able to do it by now, that if I start a car engine, the car moves 5 times 10 to the 20th electrons. How many coulombs of charge are moved in doing this? Well, I know an electron has 1.6 times 10 to the minus 19. So I say 5 times 10 to the 20th times 1.6 times 10 to the minus 19. That is coulombs per electron. This is number of electrons, the 5 times 10 to the 20th. And that's equal to, what is that? It's 80, right? I think it's 80. 80. And because it's electrons, it's going to be negative 80. So E is the right answer. You get a pretty big current when your car first starts up. Don't ever touch it. It smarts. Okay? Yeah, Megan?
Somewhere it tells you what the material of the object is and you have to figure out its charge. Like it'll say if it's conductive or
Like a calculation type thing?
no. Or you just say if it's positive, negative, or neutral.
Oh, yeah, I think I know what you're talking about. Let's see. We can come back to some of these. Like one of these,
Yes,
but more complicated. Oh, that's the last one. Let me go back up to the top. Like number 2. Is that one of those types of problems where I'm looking to figure out what are the charges? Regardless, number 2 is a good question. Can we do number 2? And then we'll go through it. This is spring 20, so last year's exam. And in this one, it shows 2 cubes, 1 and 2, that are attracted to each other. Already we know that cube 1 and cube 2 have to have opposite charges, right? Let's just assign them a charge. I'll say this is negative and this one's positive. And so now I want to know if cube 3 is a neutral conductor, which of these scenarios will occur? Huh? E is not a bad answer, but E is not the right answer. E is sort of right, but not exactly right. And I want to venture another guess, or C. Right? Remember we talked about how if I have an object that is a conductor, and if I have a charged rod that comes up next to it, that on the conductor, I get negative charges over here and positive charges over here. And even though this is neutral, right, no net charge, that I still get an attractive force between these two because I get this polarization of the charges on that conductor. So two things are important. If it just said neutral, you would be right. E would be the right answer. But it also says conductor. And the conductor means that C is the right answer because I would have a negative charge here and a positive charge here as I assign them up here. And that means that I would get a polarization of charges there and a polarization of charges there, meaning that they would attract to one another. I'm not sure that's exactly what you're looking for, but it's still a good question. Yeah. Let's try this one. Number 1. So spring 20 still. Charge Q is a distance D from charge plus Q, and twice that from the charge minus 2Q. Which of these vectors best represents the force on Q? You want to draw the vectors on the charge Q, the one with all the arrows coming out of it, such that they are in the right direction and they have the right relative sizes. So the force towards or for this charge will be attractive or repulsive? It's going to be repulsive, right? Now I have a bigger charge. It's twice as big. That force is not going to be repulsive. It's going to be attractive. Is the vector going to be twice as big? How much bigger, or rather, how much smaller will the vector be? What relative size will that vector be? I'm going to write Coulomb's law, KQ over R squared. I have a distance that is twice as big, and I have a charge that is twice as big. I've doubled the charge, and I've doubled the distance for my minus 2Q charge. So my force is going to be 1/2 the original force. You'll see how that worked? Because I have a 2 over 4. And so that means this vector is 1/2 the original size, the size of this vector, which means the answer is what? D. Now, you didn't really have to know the exact relative size that is half the force of the other, but on some other questions, that might become important. Okay? Tell me about number 4. I have a proton and electron. Proton, electron, they're separated from one another. They were released from rest. Which will experience the greater acceleration as they move towards one another? They will move towards one another, right? Will be the proton, the electron. Will they experience the same acceleration, or does it depend on their distance apart? Now, remember Newton's third law. Newton's third law is every force is an equal and opposite force. We talked about that with regards to Coulomb's law. But which one will feel the greater acceleration? Both will feel the same acceleration because you're thinking they both have the same force, right? If I have my proton and electron, they're both going to move together like this. But don't forget that your proton is at more, less, or the same mass as an electron. A lot more, right? Like, what is it, like 10 to the minus 31 for electron, I think? Is that? Is a lot. It's like 10 to the 10th times more massive. It's a lot more massive. And so my proton is like over here, and my electron is like over here. The proton just doesn't move very fast because it has a lot of inertia. So that means that the electron is going to zoom over. It has a much smaller mass and much less inertia. Okay? Don't forget the masses. Those masses, by the way, are on your equation sheet. Okay. Let's do number 7. What is the direction of the 4 nanocoulomb charge acting on the 4 nanocoulomb charge? What is the direction of the force acting on this charge? Attractive or repulsive? It's an attractive force, right? Can you tell me what this angle is? It's an equilateral right triangle. 2 and 2 here and here. So that is 45 degrees. Now, if it's 45 degrees, it's what with respect to which axis? The negative x. So 45 below the negative x. Let's go see what our options are. Oh, it looks like I have that option. So it's 45 below the negative x. But you recognize that these others are all different. That 135 from the positive x, A, would be right here. That's 135. 45 above the positive x would be right here. That's option C. And then D and E are just, they're different angles. They're nothing like 45, so I don't even look at those. Okay? On the quiz, a question like that. On our test, it'll be similar to that, but a free response where you have to work it out. Oh, Megan, maybe you were talking about something like this. Okay. Well, what would be the distribution of charge on this one? B, right. So, yeah, be careful. Because I have this positive charge over here, I get negative charges, like all the electrons rush over to that side of the conductor, and I'm left with positive charges over here. So that gives me B as the right answer. Emily? Yeah, so if they touched, all the charge would redistribute it. So if they touched, I would have, and then they come back apart, I would have a half Q and a half Q separated. Okay? We saw that in that previous problem. Electric field. Can I just introduce electric fields? Is that okay? It's really a lot like what we've been doing, and I'll let you go in about 5 minutes. Okay, I know y'all got Friday afternoon plans, whatever you're doing. What are y'all doing on Friday afternoon? Study, right? Y'all study. So let's just preview electric fields a little bit. Remember, F is KQQ over R squared rather. An electric field is a force per unit charge. The way that I determine the direction of an electric field, say I have a positive charge right here. If I want to know the direction of the electric field, I take what I call a positive test charge. My high school physics teacher always said, you carry 2 things in your back pocket. You carry your right hand for the right hand rule, which we'll see later. We introduced it last semester, but right hand rule, right hand, and you carry your imaginary positive test charge. So wherever you go, you always have your right hand and you have your imaginary positive test charge. That test charge is imaginary, it doesn't actually exist, and it's positive. So here's my positive test charge, Q naught. If I want to know what the electric field is, I first ask, what is the force on that charge? There is a repulsive force due to that blue charge. That force, the direction of that force, is the direction of the electric field. So the electric field is in that direction. I can move that positive test charge all around and figure out what is the electric field all around this charge. We had gravitational fields too. Gravitational fields were a force per mass. Do you know what a force per unit mass is with respect to the Earth? What is force per mass? Huh? Acceleration, right. This is G, right? F equals mg. this is our gravitational field. We didn't call it that because, I don't know, we didn't need to. But now that we're talking about electricity, electric fields are pretty important for us to understand electric fields. Because we'll use electric fields for a lot of things. They use electric fields to treat cancer. They use electric fields to move particles around, like move atoms around in particular places that you want them. They use electric fields for your inkjet printer. They use electric fields for all sorts of things. And so it's important for us to understand what electric fields are. Because electric fields are a force per charge, that's going to be KQQ over R squared divided by a charge. So the expression is going to be KQ over R squared. That is our expression to find the electric field due to a point charge. Okay? We'll get into calculating all that business on Monday. We're going to do electric fields. It will be on the quiz. So if you're practicing over the weekend, you can look back at some of the videos. New people to my class, I guess it's just y'all too, right? Oh, you're new too. Oh, you were in my lab last semester. So I have a whole website with a bunch of videos for exams and stuff. That's linked from the course website. You should be using that to prepare for the quiz. Okay? Quiz should be 100% everybody because you know what all the questions are. There's a bunch of questions, but if you can just master that subset of questions from chapter 1, forces and fields, you'll make 100% on that quiz.